Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are wrapping up Chapter 6 in our textbook, Thermodynamic Models of Real Pure Compounds, and we will be looking at residual properties in this lesson. Residual properties are defined generically as the difference between the actual property and the ideal gas property at the same temperature and pressure. If you designate the generic property to be M, where M could be any property, it could be volume or it could be enthalpy, anything. The residual Mr, using a superscript, is equal to M minus M at the ideal gas state. So for instance, Gibbs energy, GR, is equal to G minus G for the ideal gas. Or residual volume is volume minus the ideal gas volume. That one's nice because we know ideal gas law, V is equal to RT over P, so V residual is V minus RT over P. I also can, however, factor out the RT over P. Now that may seem crazy, right? But if you do this, V is multiplied by RT over P and P over RT, right? That's just multiplying by 1 in a really crazy way. Therefore, when I factor it out, I end up with the RT over P coming out and V times P over RT. This is, by definition, Z. Z is the compressibility factor. So VR is equal to RT over P times Z minus 1. Now we can do similar things for any of our properties. Why? Why would people bother doing this? Well, okay. We can do our calculations in steps. In our mass and energy balance course, we're taught to that we can choose any path we want if something is dependent only on the initial and final state. And so one of the things we can do is have a state, or a process rather, where we turn things into an ideal gas, do all of the process as an ideal gas, and then convert it back from ideal gas to the real material at the very end. These steps in this hypothetical path do not need to be real, and so this makes it easier to do our calculations. If I know how to do things for an ideal gas, I can do 99% of the work as an ideal gas and use these residual properties to convert my initial and final state. It's interesting sometimes to visualize this. If I want to know what's happening as I go from state 1 to state 2 for property M, delta M would be the change between these two, right? However, I can choose any path. So, for instance, I could take this to the same temperature and pressure, but as an ideal gas. I could then go to state 2 as an ideal gas, and then finally convert it back to the real substance at state 2. This change from M1 to M1 as an ideal gas is the negative of M1 residual. This change from M2 ideal gas to M2 is M2 residual. And the change from M1 to M2 as an ideal gas is just delta M for the ideal gas state. And this process could be as complex as we want. Therefore, delta M is going to be delta M for the ideal gas plus delta M for my residuals. These residual properties are written in your book, and they derive them using the things that we've been doing earlier in the chapter. So I'm not going to do that again. I think you guys can read the book on your own, But these are the summaries of the various equations. They end up with u minus uig, so u residual is RT times 1 minus z plus the integral of v minus t dv dt at constant pressure dp. So all I need to know here is v, t, and p, how they're interrelated, and z is RT. H residual is the integral for change in pressure from the ideal gas state, P equals 0, to the actual pressure, of V minus T dV dt at constant pressure dP. And delta S is the negative integral from the change in pressure of dV dt at constant pressure minus R over P dP. Now when they use Z, Z is equal to PV over RT. If we want this as a function of T and V, right, depending on the equation of state we have, that may be more practical. We have these expressions. U residual is the integral from the ideal gas state as V is infinity to the real V equals V of T dP dt at constant volume minus P dV. Delta H, or H residual rather, is RT times Z minus 1, the integral from V equals infinity to V of T dP dt at constant V minus P dV. And delta S is R ln of Z plus the integral from V is infinity to V of dP dt constant V minus R over V dV. These are in the book. There's some great examples in your book. In particular, I really recommend that you look at examples 6.9, 6.10, and 6.11, where they demonstrate the use of these. We'll do one example. Gas flowing through an adiabatic compressor. It's at steady state. It enters at P equals 1 bar and T equals 400 degrees C and leaves at 3 bar and 500 degrees C. We will assume the compressor is reversible and want to know what is the work required to operate this compressor. We will assume the gas has a constant heat capacity of Cp equals 40 joules per mole Kelvin and follows the equation of state V equals RT over P plus A times PT. The units are given as volume in centimeters cubed per mole, pressure in bars, T in Kelvin, and A has the value of 0.010 for this particular case. So, a couple of things that we need to do. First is we need to figure out Z. That's going to be important to us. Z is PV over RT. So I can simply take this expression here, okay? And if I do that, then multiply through by P over RT. The first piece is 1, and APT times P over RT says Z is equal to 1 plus A P squared over R. Okay? Z is a function of pressure, the way this is written out, okay? Not temperature, but pressure. Now, I want to figure out the work. Work for this reversible, adiabatic, therefore isentropic compressor is going to be delta H for the residual plus delta H for the ideal gas. Delta H for the ideal gas portion is really easy. It's C sub P dt from T1 to T2. Delta H residual, well, let's look up our formula. It says that it is V minus T times dV dt at constant P dP from T1 to T2. All right, V these are from P's, excuse me. V is RT over P plus APT minus T times dV dt at constant P, and I'll take that derivative. So P is a constant, R is a constant, A is a constant. All that's varying is T, so R over P plus A times P dP. All right, RT over P, those cancel out. APT minus APT, those cancel out. Therefore, delta HR is equal to P1 to P2, 0 dP, therefore 0. WS is simply then the integral of C sub P dt from T1 is 400 degrees C, T2 is 500 degrees C, 40 is C sub P, joules per mole Kelvin. Delta T is 100 Kelvin or degrees C. Remember, delta T is the same in either one of those. Therefore, this is simply 4 kilojoules per mole. Now, obviously, there are more complex examples, but again, you can read those in your book or try them on your own. But this is the process that you need to follow. So this concludes Chapter 6, and I thank you very much for your time.